Now let's turn our thoughts to energy. So we have this disk that's spinning. So obviously it has kinetic energy, but how do we calculate this kinetic energy? Because different parts of it are moving at different speeds. So we're looking at rotational kinetic energy in this case because it's not translating. So in answering this question, instead of looking at the entire disk, let's just look at a tiny section of the disk. So this is looking at that tiny section spinning around. So if we're looking at this tiny section of it that could just break free, if it broke free right about here, it would take off tangent to the circle, and of course it would have a kinetic energy of 1/2 mv squared, whatever that tangential velocity is. Well, we know tangential velocity is equal to r omega, so therefore the energy of it must be 1/2 mr squared times omega squared. Well, mr squared is really the rotational inertia of that while it's moving in a circle. And so the rotational kinetic energy of this as it's moving in a circle must be 1/2 I omega squared. Now let's think of many of these together. Well, they all would have some rotational kinetic energy. So how would I figure it out? Well, I must figure out what the total rotational inertia is, which would be summing them all up. Now imagine it's the disk. Same idea. Sum it all up, except you'd have to do it through calculus. So we get our next equation for kinetic energy, and notice the kinetic energy for rotational looks very similar to the kinetic energy for linear situations. So linear is 1/2 mv squared. Rotational to 1/2 I omega squared. So I is the rotational equivalent of mass, and omega is the rotational equivalent of velocity. So let's look at the case of this ball and this block going down this ramp. Notice there's no friction, which means the ball will not rotate, it will just slide. And so we have Eg equals Ek, solve this, and we end up getting a speed of 3.2 meters per second. Do the same thing for the cube, and we get the same answer. So this is when there's no friction. That means at the very end of the ramp, the ball will not be rotating. It's just sliding down the ramp. Okay. Now, let's try it to see what happens when it starts to rotate. That means the friction is not zero now. In this case, let's do a hoop instead of a ball. If I'm looking at this, there are some forces that we should think about. There's a weight acting right at the center of the thing that's straight down. Well, it doesn't have any lever arm. The R is zero because it's spinning about the center of this. So it does not cause a torque. The normal would be straight through the center. So again, it doesn't have a lever arm. So the R is zero. Or you could think of it this way, normal times that radius, but the angle would be 0 degrees, so sine of 0 is 0. So there's no torque from it either. The only force that's going to cause a torque, a spinning, is friction. And so that's why I'm saying the coefficient of friction is not 0. So let's assume there's no sliding. That means it's only going to be rotation all the way down. Okay. So for hoop, I is mr squared. So the gravitational energy at the top, at the bottom, it's going to be it's going to be stored in two accounts, the translational kinetic energy account and the rotational kinetic energy account. So I have mgh equals 1/2 mv squared plus 1/2 I omega squared. And I can go ahead and plug into this. It tells me that the mass is 2 kilograms. So for I, it's going to be mr squared, so 2 kilograms times r squared. Remember that omega is v over r. So I could plug that in as well. The r squareds are going to cancel. And so I can then solve this. And I got a speed of 2.2 meters per second.